here's our next circuit to solve. It looks a little complicated off the bat, but once we boil it down to its components, I think you'll see it's pretty easy to simplify. We start with a battery. In this case, our source is 90 volts, and we've got a couple of different loads. Our first load is just R1 in series with the battery. Our last load is R8, also in series with the battery. But then we have this really messy region here. A good thing to remember, just looking at this circuit, is that the potential difference across these 2 points is constant. It's just one potential difference, one voltage drop. So the potential difference across each single branch is exactly the same. So what we can do is we can boil this down to an equivalent resistance using our rules about getting equivalent resistances, and that will help us simplify the circuit. Now if we look at this circuit, we know the voltage drop across R1, and we actually know the current through R1 and R8. It's 3 amps. So something we can do right off the bat is we can figure out what R1 is. R1 is just equal to the voltage drop across it divided by the current through it. 30 volts divided by 3 amps gives us 10 ohms. So that's something we can do right off the bat, which will help us later on. Now the first thing I'm going to do is I'm going to simplify this circuit. And the first thing I'm going to simplify are the resistors on these 3 branches. So I'm going to redraw the circuit below. There's my source. R1 is going to stay the same. But now this 3-branch system is only going to have one resistor on each branch. So here's R1, there's R8. I'm going to call this equivalent resistance on the top branch R23. This will be R45, and this will be R67. So every single branch had 2 resistors in series. So the equivalent resistance in series is just summing those resistances. So R23 is R2 plus R3, which gives me 30 ohms. R45 is just R4. Oops, let me try that again. R4 plus R5, which in this case is just 15 ohms. And R67 is R6 plus R7, which in this case is 10 ohms. So that's one step in simplifying the circuit. The next step is to simplify these 3 branches into one equivalent resistance, which I'll call R27 for lack of anything more inventive. Here's the battery again. R1 is going to stay put. I'm going to draw one equivalent resistance, which represents all 3 of those branches, and below R8 stays the same. Now R27 is an equivalent resistance of 3 resistors that are in parallel. So I'm going to have to use my parallel equivalent resistance rule. 1 over R27, sorry that's an equals 1 over R23 plus 1 over R45 plus 1 over R67. So 1 over R27 is just equal to 1 over 30 plus 1 over 15 plus 1 over 10. I'm going to substitute that in my calculator. I'm going to take the inverse of that sum, and I'm going to get R27, which is equal to 5 ohms. Okay, now I know R1. We found it at the very, very top. It was 10 ohms. I know R27 now. That's just 5 ohms. I don't know R8, but from the very top, what I was given the total current is 3 amps, and I also know that the total voltage is 90 volts. So one thing I can do at this point is I can apply one of our Kirchhoff laws. And I'm going to use loop A to sum all of the voltage drops and voltage gains. So in loop A, I know that the gain in voltage across our source is equal to the voltage drop across resistor 1 plus the voltage drop across resistor 27 plus the voltage drop across resistor 8. What I also know is that the voltage drop across I1 is I total times R1. This is I total times R27. and this is I total times R8. Now the one thing in this equation I don't know is R8. So when I substitute in some values, I'll be able to solve for R8. I'll factor out an IT to make everything a little neater. And now I can just substitute in some numbers. The total voltage across the battery is 90 volts. My current is 3 amps. Resistance 1 is 10. Resistance 2.7 is 5. And resistor 8 I don't know. So rearranging and solving, I can find that resistor 8 is actually just 15 ohms. That's resistor 8. Now that I've found that, I can start working backwards. The first thing I'd like to also find, since I don't know much in the circuit, is I can also find the voltage drop across resistor 8 pretty easily. That's just equal to the current through resistor 8, the total current, times the resistance of resistor 8. So multiplying those two numbers together, 3 times 15, get a voltage drop of 45 volts across resistor 8. Now the next thing I can do is I can go back to this equivalent resistance, resistance 2.7, and I can figure out the voltage drop between those 2 points in my circuit. The voltage drop between those 2 points in this circuit is the same thing as the voltage drop between these 2 points in my original circuit. So what I'm going to find right now is I'm going to go back to this equivalent resistance, and I'm going to figure out what the voltage drop is across it. That's equal to the total voltage traveling through it times that equivalent resistance. So that's 3 times 5, which is a voltage drop of 15 volts. Now that I know that between these 2 points it's 15 volts, and between these 2 points it's 15 volts, I can figure out what the current is through each of those 3 paths. And I'm going to go back to this circuit diagram to figure it out. So if I go back to resistance 2.3, this top resistor right here, I can figure out that the current going through that branch, through that resistor, is equal to the voltage drop that I just found, 15 volts, divided by that resistor, resistance 2.3. That's 15 divided by 30 ohms, which gives me 0.5 amps. Then I can do the same thing for resistance or resistor 4.5. The current through that branch is equal to the voltage drop that I just found divided by resistor 4.5. That's equal to 15. Oh, that moved. Move that back. A little more. Oh, okay. Not really working for me, so I will try writing that again. We had V27 divided by R45, which is 15 divided by 15 ohms, which is just 1 amp. And finally, R67, current through branch 6.7 is equal to the same voltage drop, 15 volts, divided by resistor 6.7. So 15 volts divided by 10 ohms gives me 1.5 amps. I'm going to double check that this all adds up to the total current going through the battery, because based on Kirchhoff's current rule, it certainly should. 0.5 plus 1 plus 1.5 all adds up to 3 amps. Okay, so that's good. Now, the last thing I don't know, the last thing I want to find out is the voltage drop across each of these resistors, my original resistors. So we'll go back to our original equation. For resistor 2, the voltage drop across resistor 2 is equal to the current through resistor 2 times resistance 2. So the current through branch number 2 we said was 0.5 amps. The resistance of resistor 2 is 10 ohms, which gives us 5 volts. For the voltage across resistor 3, we've got that same current. It's the same branch. I guess I'll call it I23 to be consistent. So that's 0.5 amps R3 was 20 ohms, so that gives us 10 volts. Adds to 15, that's good to double check as we're going. V4 is I through branch 4, 5 times resistance 4. That's 1 amp times a resistance of 6 ohms gives us 6 volts. V5, that same branch, so that same current, times resistor 5 is 1 amp times 9 volts, which gives us 9 volts. Again, adds to 15. That's always good to double check as we're going along. V6 is the current through that last branch, 6, 7 times resistor 6. That current was 1.5 amps. That resistance was 8 ohms, so that gives us 12 volts. The voltage drop across our final resistor, that branch current times resistor 7, so 1.5 volts times the resistance, which was 2, gives us 3 volts. And that's it. We solved for all the unknowns.